here I will introduce the maximum entropy approach to understand Fokker-Planck evolution. So I will start the introduction of surprisal analysis by revisiting the principle of maximum entropy. In statistical mechanics, the distribution over the phase space can be inferred based on the observed expectation values. The inference is non-unique. The unique inference can be made by maximizing the entropy. So in the resulting maximal entropy form, the observable constraints appear in the exponent of the distribution, and the lambda j's are the multipliers that imposes that these constraints are satisfied. So this approach can be generalized to evolving systems, where the evolving distribution maximizes entropy at every instant. So now all the time dependence is taken up by the Lagrange multipliers, and now we recast this interpretation in terms of surprisal. Surprisal is a log probability measure. Now we can see that the constraints of the evolution appears as a linear expansion weighted by the Lagrange multipliers. So when a set of constraints reproduce the exact distribution, then we call that the set of constraints form a closed algebra. So for reversible evolutions, the approach starting from the maximum entropy in reproducing the exact dynamics is already been established. Now I extend this analysis to the irreversible case. So I start with the simplest possible description of an irreversible system given by the Fokker-Planck equation. The Fokker-Planck equation models a system embedded in a dissipative environment. The first two terms are the forces from the environment, the other two terms are the Newtonian evolution. Now, motivated by maximal entropy, I can rewrite the dynamics in terms of surprisal that characterizes deviation from a prior distribution. So the prior distribution is the stationary solution of this equation, which is the Boltzmann distribution. So in a while I'll explain why do we shift the reference to a prior distribution. So the algebra of constraints that reproduce the dynamics can be determined from the equations of motion. For example, if I insert this expansion into the first equation, then we can see that it leads to a closed set of equations for the multipliers, and further that this set of constraints can also reproduce the exact distribution. So the first term of the expansion is the normalization constraint, and we have the expansion up to second order moments. The last term is the cross correlation, which signifies the energy transfer between energy conversion between kinetic and potential energy forms. So this way the total evolution can be replaced by the evolution of individual constraints. Since the surprisal is defined as a deviation from stationary state, the Lagrange multipliers quantify the disequilibrium present along every constraints at all times. So here I discuss the relaxation in the mean value constraint by plotting the Lagrange multipliers as a function of time. We have two known scenarios. One is the slow relaxation in the momentum, and other is the overdamped relaxation. So the longest time constant in these two kinds of relaxation determines the limiting dynamics. So this way the total evolution can be studied using individual contribution of constraints at all times. Now I proceed to the bystable case, where we have two potential wells. So a low energy population which is stuck in either of a potential well can climb the barrier when there is a environmental fluctuation. So for this problem, the expansion of constraints, so they do not form a closure. It is due to the quartic term. For example, when I solve for second order moment in P, I require fourth order moment, and it further requires sixth order moment, and there is this iteration diverges indefinitely. So therefore, we cannot have a expansion of surprisal that is finite for this general case. But yet in a high barrier limit, the high barrier limit is a physical limit of interest to Kramer's problem in relation to chemical kinetics inside solutions. So if the wells are very deep, then there are no to an excellent approximation there is no net transition. So using that, we can write maximal entropy form separately for the two wells. So here I take one correlated Gaussian for the first left well and the correlated Gaussian for the second well. So using this ansatz, we can study the evolution of the distribution using the evolution of constraints. So here I show the evolution inside the left well. So we can see that there is a time scale separation between a local equilibration of the distribution, that the distribution attains a steady value when the net flux between the wells is not yet equilibrated. So this condition is called quasi-stationarity, which is a feature of when the barrier is very, very high in comparison to a typical fluctuation. So in the long time, the net flux equilibrates and the branching between the wells achieve a steady value. So regarding this value, we provide the maximum entropy interpretation for the branching between the wells. So to do it, we group the total members of the distribution into those belonging to the left well and the right wells. Now I can write the expression for the entropy using the composition of these two subsystems. So maximizing entropy with the subject to known constraints can results that the branching ratio is just the ratio of partition functions. So for our case, when the mean energy is constrained, the branching ratio becomes as this. So in the deep well limit, when the left and the right well are just shifted by a constant given by the shift in their ground state energies. So in the high barrier limit, the population branching just becomes the Boltzmann factor, where EL and ER are the ground state energies of the wells. So what I presented is that we presented maximum entropy motivated approach to a simplest possible dissipative system. So the Lagrange multipliers, it quantified the disequilibrium along each constraints to the total disequilibrium at all times. So thus offering a detailed view of the dynamics. Knowing the constraints replaces the need to handle the large data for the distribution. So this is also useful in compaction of large data. Any evolving system can be studied in detail by identifying the set of constraints. So here I showed that 6 constraints are enough to reproduce the dynamics of a parabolic potential. Using Surprisal analysis, I highlighted the dynamics of dynamics in a double well potential. So I would like to thank my supervisor, Professor Raphael David Levine, and all my friends for their valuable time and discussions. And I would like to thanks once again to the organizing committee and you all for your attention.